All right. Okay. Let's talk about the final exam. So next week. Okay. So you'll have the full 3 hours. It shouldn't take the full 3 hours. Maybe one or two of you will be left at the end. No, I mean it's just. I mean I'm not. Oh, I'm not saying like I have anybody in mind. I'm just saying like. I'd say most finish within 2, and then some take longer. No problem. Okay. About 55 questions or 54 questions-ish or something around there. Okay. All multiple choice. It's going to start off with you're going to have 10 conceptual questions. About statistical inference. And then you'll have maybe 5 questions or so about what test is appropriate for a given scenario. And then I'll have, and the bulk of the test is going to be, here's some data, so, 35-ish questions, which is going to be, here's some data, and description, and then questions related to performing some kind of statistical inference. So something like, here's some data. If you're going to do a t-test for the t-test for independent samples, what would the hypotheses be? What would this and that be? So let's see. Okay, so all right. So I guess I'll list off. Questions that you might see will be like, what are the hypotheses? If it's a hypothesis test. Find the test statistic, or standard error, or p-value, okay, related to the test. What is the conclusion? And it's always going to be a conclusion in the context of the problem, okay? Let me just think what else. Questions kind of related to this. Maybe what a type 1 or type 2 error is in the context of this problem also. Okay, so you got a bunch of questions like that, and then you have, you know, just a handful of miscellaneous questions. Kind of maybe definition based or just some old concepts, things like that. You know, probability concepts or whatever, probability, etc. Okay, I think that's a pretty good description of what you might see. Okay. All right. Is this okay? All right. And so questions related to performing statistical inference. Okay. So maybe I'll just kind of create a list of inference methods. That we've covered in class. Okay, so let's see. Okay, so we have t-tests for independent samples. We have the t-test for paired data. We have the Wilcoxon Mann-Whitney test. For independent samples. The chi-squared goodness of fit test. The chi-squared test for independence. We have confidence intervals. For P. We've covered one-way Anova. We have correlation and linear regression. And test for significant correlation. Okay. So make sure you're comfortable with all of these inference methods. You are, maybe I'll let me flip back. You are allowed to have a note sheet, okay? You have a sheet of notes. So this will be just letter size, front and back. Yes, question?
I just used all of those parts of those notes, but if I made the whole recorded?
Hang on. Okay, so the question is, can you use note cards? Okay, let me think. Okay, yeah. Let me think how many are equivalent. 3 by 5, 15. I think you get, or 6? 6 3 by 5s, is that equivalent? I don't know, wait,
You
let me
said
think.
3 last time for the half page.
For
You
the,
said 6.
so it'd be 6 if it's front and back.
Yeah.
Okay, yeah. Because you get 8.5 by 11 times 2. So you get 187 square inches if it's letter size sheet, front and back, and then 3 by 5
It's slightly less.
times 30, yeah. Okay, so you get a little bit less if you go 3 by 5 route, but no, I don't think anyone's going to complain, so. So 6 3 by 5s front and back, or 1 letter size paper front and back. Up to you. And it can be typed or whatever. Just make sure it's your own creation, okay? All right. Any questions on this? You know, bring your calculator, your reference tables, your pencil and eraser, whatever. I'll provide the scantrons and the test.
And you want us to bring this one to the...
Yeah, bring your reference tables, yes. Yes, bring your reference tables, yes.
So the final grade emphasis more on the stuff that we covered after the midterm?
Yeah, it's gonna have, this is the breakdown of the final, so, pretty much everything prior, you know, I think after the midterm was where we really got into statistical inference. We did, I guess, oh, I should add just plain old confidence intervals for mu, right? So CI for mu, and then CI for mu1 minus mu2. So I know these two inference topics were covered prior to the midterm, so I guess this would be covered in the field of inference. But I'd say everything prior to the midterm, I think, was kind of preparing us for inference. All of this just descriptive statistics and probability and sampling distributions and all of that. That was to prepare us for inference, and then the second half was all focusing on statistical inference. And so, yeah, the final will have definitely a focus on statistical inference. What's that?
Is there a lot of Z-scores and stuff like that?
No, not a whole lot of Z-scores. So, yeah, after the midterm, we haven't really used the normal table so much, huh? So, there are statistical inference methods that use the Z table, but we haven't really talked about them. So, okay.
Will we get the F table provided to us?
I'm not going to have any questions that rely on the F table, so I will not provide it, but I will not ask anything about it. Okay, so let me talk about when would we use each test. Oh, okay.
Is like the binomial distribution and that stuff gonna be on it, or is that just...
No.
Okay.
No binomial. Well, maybe I should put something on. I should not. Okay, but huh? No, our staff. Okay, so when would we use each test? Okay, so we have to. I guess the first question is what type of variable is our response. Okay, so the response are basically just what is the variable that we're performing inference on, okay? And so we want to know what type of variable is this. So if it's categorical versus if it's numeric, our choice of inference methods will be different, okay? So so if we have a numeric response, we'll have a set of tests, and then if we have a categorical response, we'll have another set of tests. Okay, so let's talk about what happens when we do a numeric response. Okay, so the next question is there a predictor, and if there is a predictor, what type of variable is our predictor? Okay. And then if yes, what type of variable? Okay. So let's say we have a numeric response and no predictor variable. Okay. Then the inference method that we perform here is basically we just have a sample of data, a sample of numeric data, and we want to perform some inference based on our numeric data. So what can we really do here? We would have a confidence interval for mu. Okay, we can create a confidence interval for mu, and this will tell us kind of plausible values of the population mean, and that's what we got. Okay. Okay. If we have a numeric predictor, all right, what is the inference method we can do here? Numeric predictor, numeric response. No, numeric predictor. So what does it mean to have a numeric variable as the predictor? So this is this. Okay. Maybe. All right. Let me just. I'll just give you the answer. This is what we covered last week with correlation. Correlation/linear regression. Okay. We have a numeric predictor x variable, and we have a numeric response, or kind of our y variable in that case, right? So x and y are both numeric, and we're looking for a relationship between them. That's going to be correlation. Okay. And then lastly, we have the categorical predictor. Now, throughout the course, I haven't really taught the concepts as a categorical predictor and a numeric response. Okay. So far, it was mostly just like we have these numeric values, and we're seeing if there's a relationship between the numeric values and the grouping variable. But if you think about what a grouping variable is, it's just it's a categorical variable. Okay, so we have a few things to talk about here. With categorical predictors, we can talk about if we have only two groups or two categories, we will have a bunch of stuff. Let's see, I'm going to run out of space on my screen here. Okay, well, I'm going to stop going horizontal. I'm going to just have to go vertically here. Okay, so with two categories, we can have independent groups. Okay. And with independent groups, we have a few options, okay? With the independent groups, we can have t-test for independent groups. And also confidence interval for mu1 minus mu2, okay? So this is basically, we've got two categories. This would be something like, I think the example in the book was something like, you know, is the norepinephrine levels in the mice different if the mice received toluene versus control or something like that, okay? So you got two categories, okay? It's one categorical variable, whether they got control or the treatment, and then you want to see if there's a difference in our numeric response of norepinephrine levels, okay? The other option is if the data is not normal, what do we do? Can you guys read that? If the data is not normal, what's the test we would use? To see if there's a difference in our numeric response, this is going to be the Wilcoxon Mann-Whitney test. Okay, so if your data is not normal and you've got, you know, small samples, do you remember when we used our Wilcoxon Mann-Whitney test? Okay, so small samples, and we've got like outliers in it, okay, indicating that the assumptions about the central limit theorem don't work here. Okay, so in that case, we would use the Wilcoxon Mann-Whitney test. Okay, so that's with independent groups. If we don't have independent groups, we would have paired data. And what do we use when we have paired data? Paired t-test. There you go. That is correct. Okay. So two categories. Okay. All right. So that's with the categorical predictor, covering two categories. And then if you have more than two categories, so I'll say 2+ categories, then what is the inference method that we've covered? No?
No, Anova.
One-way Anova. One-way Anova. So one-way Anova.
I thought two-way ANOVA was more than two categories.
Okay. All right. Let me. So one-way Anova is a numeric response and one categorical predictor with two or more categories. So if you have three categories or something, remember it's a categorical predictor. So this is something like so the example we covered in class was the numeric response was how much weight did the lambs gain. Okay, weight gain of lambs. That's a numeric response. Okay, and then we had a categorical predictor, diet 1 or diet 2 or diet 3. They were in categories. Which diet the lamb received is a categorical as a category. That's what separated our three groups, and we had a numeric response. So what's going on here? Okay. All right. Is this okay? All right. And then so, you know, what about two-way ANOVA? So two-way ANOVA is not going to be covered on the final. That would be a numeric response with multiple categorical predictors, okay? So all of these, we're just having, you know, one predictor, okay? Two-way ANOVA would be like multiple categorical predictors.
When you're saying predictor, like you mean like variable?
Yeah, like a variable that we are using to make conclusions about the response, okay? Like, does this thing over here affect this numeric response, right? So if we're looking at the weight gain of lambs, does this thing over here, whether maybe it was just diet 1 versus diet 2, does the diet make a difference on the weight gain, okay? And so when we started off with t-test for independent groups, that was what we had. We had like, I think examples in the book were, is the like flexibility, torsion flexibility different for, I don't know, dancers and whatever other group, gymnasts or something like that, okay? You know, you've got some numeric response, which would be like flexibility as expressed as a number, and then you have a, quote, categorical predictor. And when we first introduced our topic, we just said we've got two groups. Is there a difference between two groups? But you can think of it as, you know, how did you define the two groups? You know, maybe it was defined on gender or something like that. And so now the question is, you know, does this variable, categorical variable, have an influence, or is it associated with differences in the numeric response? Okay, so that's the what we have with the numeric response, and then we have also, you know, what do we have when we have a categorical response? Okay, so with a categorical response, we've got the same question: is there a predictor? And we've got no predictor. And then we'll have, I'm going to go a little bit out of order here, categorical predictor, and then numeric predictor. Okay, so we have, so for the categorical response with no predictor, what do we do here? Okay, if we have what we call a dichotomous response, okay, dichotomous meaning just a yes or a no, just there's only two possible outcomes, we can perform a confidence interval for a proportion P. Okay, so that would be with a dichotomous response, okay? And then if we have two or more categories, okay, because we just have a categorical response, right? And if we have two or more categories and no predictor, what is the test we use here?
Chi-squared.
Chi-squared what?
Goodness of fit.
Chi-squared goodness of fit. Exactly. Okay? Thumbs up there, all right? So this would be, so this is chi-squared goodness of fit. If you have two or more categories, we don't have any predictor. We just have certain categories, okay? And we have just kind of proportions in mind for the categories. There's no no predictor. We just want to know, hey, is this proportion reasonable for these categories? That's what we have.
Comparing them to observed
Yes.
values.
Yes.
So would those not be numeric predictors of?
Well, so our response, we are counting how many observations we have in a certain category, okay? but the variable itself that's being recorded is categorical. Okay, so when we summarize our data, it looks like it is a number because it's a count. We've counted how many people are male or how many people have brown hair or something like that. But as far as the raw data being recorded, it'll be the variable gender. That's a categorical variable. The variable hair color is a categorical variable, whereas the variable weight would be numeric. So here we have a categorical response, and if we're doing something on gender, we could do either confidence interval for the proportion of men in the population, or a chi-squared goodness of fit test to see if the proportion of males and the proportion of females match our preconceived notion of what they should be. Okay. All right. If we have a categorical response and a categorical predictor, what is this? Huh?
I don't know, I'm guessing linear regression.
No, linear regression is numeric response, numeric predictor. Okay? So here we've got the chi-squared test for independence. Are these two categorical variables independent of each other? Okay. And this is pretty much everything we covered. And just for completeness, I'm going to throw this in here. We haven't covered this, but if you have a categorical response and a numeric predictor, this is logistic regression. And if this is, with two categories, and if you have more than two categories, this is called linear discriminant analysis. It's just a fancy name for the same thing. So we haven't covered that. I guess I'll just write not covered. So don't worry about those topics, but everything else we've covered, and this is just like a small slice of statistical inference methods. I have to say, like you can go to a library, well, maybe not any library, but an academic library, and probably find a handbook on statistical tests, and there'll probably be like hundreds in there, each with kind of like, this is the scenario you should use these in. These are kind of just like the broad basic ones that are based on what kind of numeric response do you have, what kind of predictor do you have, and then there's tons of others like, oh, is your predictor like this, and does we observed a little bit of kind of like how this further splits into there's a scenario where the Wilcoxon Mann-Whitney test is appropriate versus the t-test for independent groups and the paired data t-test and things like that. But these are just kind of very broad but useful statistical inference methods that we have. Okay. All right. Does this feel okay?
I'm a little confused on what predictor.
What a predictor is. Okay, so yeah, I know throughout the course I haven't really presented these tests as this is the predictor variable and this is the response variable. We generally said here's our data, and until we got to chapter 9 and 10 with the chi-squared tests, it was almost always numeric data, okay? And then we would just say, is there a difference in the means between these two groups, okay? We could frame that same question, right? We could take the same question, is there a difference between the means of this group and this group? and we can just say, okay, well, what is this grouping variable? Okay, and maybe it was the variable is, did they receive drug or placebo? Okay, and we could reframe the question to say, is the is blood pressure is it what am I trying to say? Oh, does the drug have an effect on blood pressure, or is there a change in blood pressure associated with the drug? Maybe we don't want to go so far as saying a cause and effect type of thing. So that can just kind of rephrasing that question almost sets it up in a response and a predictor. Okay, the predictor being, did they get the drug or not, and the response being, the blood pressure or pulse rate or whatever numeric variable we're looking at.
So would that be a categorical predictor with a numeric response?
Yes, that would be a categorical predictor, because what we want to know is, does this thing, whether they got the drug or not, does that have any influence on the response, being blood pressure or heart rate or whatever it might be? Okay. Maybe we'll take a look at some examples, and I think that will help us see a little bit better here. Okay, so I'm gonna just pull up my digital textbook here, and let's see. I'll keep going. Okay. Alright, let's see. Okay, so we'll look at this problem, 13.2.1, and it says, researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine and others were given haloperidol. Okay? After 1 year, 61 of 163 patients in the clozapine group showed clinically important improvement in symptoms, compared with 51 out of the 159 in the haloperidol group. Identify the type of statistical method that is appropriate for these data, but don't actually conduct the analysis. Okay. All right, so does this, is that good with everybody? I'll give you a minute to think about this. Do you have an answer?
No.
Oh, you have a question. Okay.
Are you gonna press the lecture notes?
Did I not do that? Oh man. Okay. You guys gotta email me when I'm not doing my job here. Okay. I will.
Okay.
Yeah.
So you post what?
The lecture notes. Apparently, I didn't post the lecture notes from last week, so my apologies. Yeah, last week I was just crazy busy with getting all of this stuff. It was the last week on main campus, and so it was just busy, and I forgot to do a bunch of stuff.
Your class
Finals are done for main campus, so it's actually spring break next week, but I get to come here and give you guys finals, so it still feels like a vacation, just because as far as my job goes, finals week is easy, because you guys have to study, but I don't have to do anything. I just have to make photocopies, and my job is done, so. Okay, do we have an answer for this? Yeah.
Is it a paired t-test?
It's not a paired t-test. What?
Correlation. No. Okay, it's a numeric response.
Okay, the answer is chi-squared test for independence.
That's what I guessed.
Okay, okay. Well, you guessed correctly, and maybe the others of you might need to just review that chart. Okay, so let's think of what is the variable that we're interested in.
Improvement in symptoms.
Variable of interest. Okay, this is the variable of interest, which would be our response, is improvement in symptoms. Okay, how is improvement in symptoms recorded? It's recorded as categorical. Just showed clinically improvement in symptoms or no, right? So basically, this is a yes, improved, or no, did not improve. Okay, so this is categorical. Okay, and what do we want to see if this is related to what? We want to see if the two drugs make a difference in improvement. Okay, so our quote predictor variable, or the variable that we want to see that could be related, could be associated. So our predictor is which drug did they get? Okay, which drug was given, and this is also categorical. They got. I don't know anything about these drugs here. I think haloperidol is a pretty strong drug, though. I don't know. I have no idea. Okay, so this also is categorical. Okay, so we have categorical and categorical. So if we go down our little guide for inference methods, it says, oh, this is categorical, chi-squared test for independence. Okay, and what this would end up looking like is we would create like a 2x2 table. Okay, and this is improved, did not improve, and this would be clozapine, haloperidol, and it says after 1 year, 61 in the clozapine group, so it would be 61 out of 163, and then 51 out of 159. And so if there's 61 here, then that means there has to be, what, 102 here. And if there's 51 here, there has to be 108 there. And so we would have, what is this, 112 and 210 and 322, I think. Something like that. Okay? And so this would be our observed data. And then you'd have to create your expected table, and then you could do a chi-squared test for independence, right? And then chi-squared. Observed minus expected squared over expected. Okay, and that's how we would do this statistical analysis here. Yes?
In this case, you'd be testing whether the fact that they improved or did not improve is independent from the drug?
Yeah, we want to know is improvement independent of the drug received. Okay, so the null hypothesis here would be improvement is independent of drug given. Okay, and then the alternative would be that one of these drugs is more effective than the other, basically, in terms of producing improvement. Okay.
So that would be non-directional the way that you.
Yeah, the way I've written this is non-directional, okay? Because I didn't specify which drug, okay? If I wanted to make it directional, I would just write something like clozapine is more effective than the other in producing improvement, or haloperidol is more or less effective, whatever, you know. The way I've written it, this would be non-directional, yes. Okay? All right, let's try another. Yeah.
Before we move on, since the final's out of 70 points and we have about 55 questions.
Did I say it's out of 70 points?
Oh, I don't know.
It's
It
even
just on
51
the
points.
canvas, it says it.
Is that what it says?
Yeah.
It says 51.
It's at
51.
51. Oh, okay.
Okay, well,
So are we having like 4 extra credit points?
probably like 2 or 3.
Okay.
Okay? Something like that. Huh?
I'm thinking of my chem class.
Okay.
Out of 70.
It's out of 70. All right.
So basically on the final, we have to figure out what test, like, method we have to use. Like, if.
Okay, yeah, okay, so I have 5 questions specifically related to which test is the appropriate test to use. Okay? I've got 5 questions specifically related to that, whereas the rest of the questions, it's like you can't write a test and ask like which test is appropriate to use without asking follow-up questions that give away the answer, right? Like I can't be like, which test should you use? Now find the chi-squared statistic or something like that, right? So, yeah.
So on the remaining questions, will you tell us which test to use, or will it just be like a word?
Yeah. I'll for the remaining questions, I will tell you which test to use. There are a couple scenarios, or maybe just 1 or 2, where using the same data, I have you use like multiple tests, and like I don't know, like for the same data, you could perform a t-test for independent groups versus a Wilcoxon Mann-Whitney test. Those are both similar scenarios and things like that. So that could happen, or you could do a chi-square goodness of fit test on the same data as confidence interval for P, right? So if you've got 2 categories. So, okay, let's take a look at this one. A biologist collected data. You have a question?
Yeah, I don't remember what it's called, but remember when we made the probability chart tree?
Who?
We're
What?
gonna have questions like bound or
Oh,
this causes this.
no. I did not put any probability tree questions.
So like nothing really from before the midterm.
No calculation questions from before the midterm, okay? Yeah. I've gone back and forth on whether I should put old stuff on there, but
No, you don't need more.
yeah, I feel like there's enough content in here to make a good exam. All right. Okay. So here we got a biologist collected data on the height and peak expiratory flow, a measure of how much air a person can expire measured in liters per minute for 10 different women. Here are the data. Is peak expiratory flow related to height? All right, so we've got the height of our 10 women, and we've got the peak expiratory flow of the 10 women. So what is the appropriate test to use here?
Correlation. Is this the linear thing?
All right, let's see. Okay, what test to use? So what is our response variable? Okay, but what is it?
It's either yes or no.
So our response is, is PEF related to height? So here our response would be peak expiratory flow. We want to know, is this related to our predictor, which would be height? All right, so these are our two variable. Peak expiratory flow is numeric, and our height is also numeric. So we have a numeric response, numeric predictor. This would be correlation, yeah. Correlation slash and linear regression. Okay. And okay, and then if we were to do this test, what would we do?
We need to plot the data.
Yeah, okay, so we would plot our data, and I don't know what it looks like. We'd get something, maybe.
Then
All right.
calculate V1.
Yeah, well, okay, so we would have to calculate our correlation.
Oh, yeah.
Maybe a computer can do this for us, okay? And then what is the test to see if correlation is statistic, if this value is significantly different from 0?
It's a T test.
No, it's multiple choice, so I can't have you plot data in a multiple choice test.
It's a T test?
Yeah, so we have a t-test for significant correlation. What's the null hypothesis for this? Yeah, rho equals 0. We want to know if the correlation in the population is 0, okay? So this is basically saying correlation in the population and then the alternative would be that it's not 0 or greater than 0 or something, okay? All right, and then you get some n minus 2 over 1 minus r squared times r or something like that. I always forget the yeah. Okay. Yes, question.
Or can we consider these independent groups, like test for independence? We're trying to see if they're even trying to get correlation. Like, what's the key here? How do we get that?
So, okay, if we were to, you're asking, can we use a t-test for independent groups?
At first I thought Wilcoxon test, what it's called.
Wilcoxon Mann-Whitney?
But then there's not like really big outliers, so I assume that that's why.
Okay,
we do that.
no, so the thing is okay, so Wilcoxon Mann-Whitney requires that we have two groups, okay? And we only have one group of observations, okay? We don't have like,
Oh, okay.
we don't have women who are tall versus women who are short, okay? The height is measured as a numeric variable, okay? We could do a we could have height measured as a categorical variable. That is possible, okay? So just like age can be numeric, we could measure someone's age in years, or we could put age as categories, okay? Like, so, you know, when you look at election stuff, they always say like so-and-so candidate, you know, won over the 18 to 30 group very prominently, and the 30, you know, so-and-so only is getting support from the 65 and plus group or something like that, okay? So they've turned age into a category, all right? And that's fine, and you just have to recognize that age is being recorded as a category and treat it as such, okay? So, because that would be something like, what would that be actually? Let me think. So for the response would be whether somebody we want to know, is there a relationship between percentage of support versus age, right? So we have a categorical predictor and a numeric response. So, you know, just like, okay, so just election polling. You know, we see stuff like candidate X, you know, has 64% support from, you know, whatever, ages 18 to 29, or I'm just making up these things, and you know, but candidate X has only 42% support from ages 30 to 45 or something like that, okay? And you know, we have some other number. What's that? Oh, actually, this is not going to work because this is a summary statistic. Let me think. Let me keep thinking here. Okay. Oh, okay. So this is actually a categorical response and a categorical predictor. Okay. So this, we have the support, even though it's summarized as a percentage, this is actually a categorical response. It's do you support or you don't support, right? Support yes or support no.
Oh, so the other percentage that's not up there is the against or not support, which would be the complement 42, so it'd be what?
Yeah,
50.
exactly. Okay, and then, so what we're missing here is we're actually missing the counts, okay? So this is, so with this summary data, we can't actually do our analysis because we are missing the actual counts, okay? And this would be a categorical predictor. And what we would have is we would have, you know, age 18 to 29, age, you know, 30 to 45 or whatever it is, okay? And then here is a support yes and support no. Okay, and then you could have even more categories if you wanted, right? You could have whatever, 46 to 65 group or something like that. Okay, I have no idea. All right. What we would need though is we would need how many people were surveyed. Okay, without the number of people surveyed, our answers, we can't do the statistical analysis. Okay, so we're missing the actual counts because, you know, if somebody says, oh, I did a survey and I surveyed 5 people and, you know, they were 5 random people, but you know, candidate A has 80% support among the 5 people, you know, your answers are not going to be significant. But if you surveyed 500 people and candidate A has 80% support, that's saying a lot. Okay. Okay. All right. Let's we'll look at another example. All right. So here is a geneticist self-pollinated pink-flowered snapdragons and produced 97 progeny with the following colors: 22 red plants, 52 pink plants, and 23 white plants. The purpose of this experiment was to investigate a genetic model that states that the probabilities of red, pink, and white are 25, 0.25, 0.5, and 0.25. Identify the type of statistical method that is appropriate for these data. Okay, so Are you answering?
Yeah.
Okay, okay. I'm going to give everybody just a moment to think through this answer before you guys shout out your thoughts. Okay, so what do you guys think? Yeah, chi-squared goodness of fit, exactly. Okay, so all we have is just the response is the color of the flower. Okay, we have 3 categories. Okay, so it can't be a confidence interval. And we have no predictors. No predictors, just proportions in mind. Proportions that we expect. Okay. So that would be the chi-squared goodness of fit test, and then I think we know how to do this, right? Okay, we'll keep we'll do 13.28. So I'm just gonna copy the upper half of our table here.
What edition are these numbers?
Fourth edition. I don't have the PDF of the 5th edition, so. Okay, so 13.28, biologists were interested in the distribution of trees in a wooded area. They intended to use the number of trees per 100 square meter plot as their unit of measurement. However, they were concerned that the shapes of the plots might affect the data collection. So to investigate the possibility, they counted the number of trees in square plots, round plots, and rectangular plots. And the data are shown in the following table. What type of analysis is appropriate here? So we'll give everyone a moment to think about this. Now it looks like the same numbers are used in the 5th edition as well. All right, what do you guys think? Yeah, one-way ANOVA. Okay, our response, the variable of interest, is the number of trees. So that's going to be numeric. And our predictor is the shape, plot shape. So that's categorical. Okay, so we've got 3 categories. So we have to do one-way ANOVA. If we only had 2 categories, we would have we could do t-test for independent groups. That would probably be the appropriate one to use for categorical data. Okay. Oh. All right, so keep continuing on here. Let's look at 13.2.10, which whoops, is spread across 2 pages here. So the first one says they looked at some patients and then they gave them 2 different drugs. Okay, so 7 patients were given Demerol, and 8 patients in the second group were given an experimental drug and reported the following numbers of hours of pain relief. All right, so how might these data be analyzed? Okay, what do you guys think here? T-test, and what kind of T-test? For independent groups. Okay, how do we know that they're independent groups?
Because they're different people.
Yeah, they're different people, okay. And there's no, well, first off, we have 7 patients in this group and 8 patients in the other group, okay? So if you have 2 groups that have different sizes, there's no way it can be paired, okay? So if they're the same size, it doesn't mean that they're paired. But if they're different sizes, you definitely know that they are independent groups, okay? So we have, yeah.
How do you know not to use the Mann-Whitney?
Okay, well, so Wilcoxon Mann-Whitney would be, is suitable. It would not be wrong to use the Wilcoxon Mann-Whitney. It's just a less powerful test. So let me, let me just finish writing this and I'll talk about, address Wilcoxon Mann-Whitney. Okay, so t-test for independent groups, we've got 2 groups, or I'm sorry, we've got a numeric response, which is hours of pain relief. And then we have a categorical predictor, which is the drug type. Okay, they are independent groups because the 2 groups have nothing to do with each other, and it's very clear. Clearly so because the 2 groups have different group sizes. Okay, so there's no pairing between our data points here. Okay, Wilcoxon Mann-Whitney could work. However, I would not say that there's any clear outliers in either sample that would indicate that we should use the Wilcoxon Mann-Whitney test. Okay, it is a small sample, okay, but if there were something, I mean, I don't know, would 8 be an outlier here? Maybe, okay. Huh? I guess you could do, I guess we could see if it would count as an outlier. 1, 2, what is it? 0, 1, 1, 2, 2, 3, 4, and 8 are, so we would have what? 1, 3.5, and IQR of 2.5. 2.5 times 1.5 would be 3.75. Is that right? 2.5 times 1.5, yeah, 3.75 plus, okay, so our upper fence would be at 3.5 plus 3.75 at 7.25. So technically, 8 is an outlier. So Wilcoxon, it's not wrong to use Wilcoxon Mann-Whitney. I don't know. I guess someone could argue that the t-test for independent groups would not be appropriate to be used either. 8 is an outlier. So the argument could be made that the base distribution or the sampling distribution of a sample of the mean of a sample of 8 patients is not normally distributed. That argument could be made, and then a Wilcoxon Mann-Whitney test would be appropriate. So anyway, that's what we have. Okay, so Wilcoxon Mann-Whitney could work. 8 is an outlier. Okay, so if you want to quote be safe, you can use the Wilcoxon Mann-Whitney test. Yes?
Is there a minimal sample size for t-test in a period of 25?
No, okay. So if the population is not normal, then a sample size of 25 is generally large enough for most circumstances. However, if the population is reasonably unimodal and symmetric, any sized sample is fine.
So in this problem, we just assume normal distribution.
That's a slight risk, okay? So basically, when you use the t-test, you are assuming that the sampling distribution of y bar is approximately normal, okay? Use of the t-test suggests the sampling, or assumes that the sampling distribution of y bar is approximately normal. If this assumption is wrong, then the t-test for independent groups could mislead you. Okay? And so it might be, quote, safer to use a less powerful test like the Wilcoxon Mann-Whitney. Okay? Because using the t-test could lead to a false alarm where you think there is actually a difference between the experimental drug and Demerol, when in reality there isn't. Okay. Yes?
I have a question. How come it wasn't the CI for mean 1 minus mean 2? Sorry.
Oh, okay. The CI for mean mu1 minus mu2 is essentially the same thing as a t-test for independent groups.
Oh, okay.
Okay? So I'll write that up here. Okay? Pretty much CI for mu1 minus mu2 is pretty much the same thing. If you're doing a non-directional t-test for independent groups, they're essentially the same. Okay. If you do a t-test that's directional, then it's no longer the same. So that I think on quiz 3 we had questions basically that equated the confidence interval and the t-test for independent groups. Huh? The worst quiz? Okay.
So if it was directional,
then
use the CI.
you would not use the CI.
Okay.
Well, I have to make a caveat and say there do exist directional confidence intervals. It's not something we've covered in the course. It's not something that is very common in the literature, but they do exist. When you run R, it will spit one out. I haven't really seen anyone talk about them, but they exist. Yeah.
For the Wilcoxon Mann-Whitney test.
Yes.
If a value is the same as values in the other group, you give it like 0.5.
Correct. Ties are worth half a point each.
Okay, so for every, say there's like in the top group there, there's 2.
There's 2 number 4s.
There's 2 number 4s, in the bottom there's 1.
Yeah.
So
So
that would be
each one would count
0.5.
0.5.
And so for the bottom one, you would get 1.
Correct. Yeah.
Because-
Yeah. 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 So each tie is worth a half. So if there's like multiple of the same value, each thing that's a tie gets counted as a half. Yeah. Half a point. Okay. Okay. All right. Do we feel okay about all of this? Yes.
Like, what's a question we could ask ourselves when we're trying to figure out the predictor in general? Because, like, that's the...
Which ones? Wait, what do you like? What is the
when
predictor?
We're trying to figure out what the predictor is.
Okay.
What can we, like, ask ourselves to, like, figure...
What's the variable of interest is really what the response is. Like, what is it that we're measuring?
Okay.
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 What's the variable that's being measured? That's a good way to think of.
That's the response.
That's the response. Okay. And then
How are we measuring? Like...
yeah, how are we measuring it? Okay. And if the and what you could and the way it's measured is important, okay? Because if we could take something like weight, or maybe not weight, but BMI. So BMI is traditionally a numeric variable, right? You got a BMI of 22, you got a BMI of 29, whatever, okay? That's traditionally a numeric variable, but we could categorize it, okay, into underweight, normal weight, overweight, and obese, and I don't know, whatever is beyond obese. And so these, so we could, we could ask, is, I don't know, calorie consumption, no, that would not be a good one. I don't know. Is gender related to BMI, okay? So if we have gender and BMI recorded as a numeric variable, then that would be a t-test, okay? Because you got, assuming just 2 genders, okay? Then you got 2 categories, and then BMI being numeric, we would have a t-test. However, if we decided to record BMI as a categorical variable, underweight, normal, overweight, obese, then, and we asked, is it related to gender, then that would suddenly become chi-squared test for independence, because now you have 2 categorical variables. So the way the variable is recorded is important. So maybe I'll write that. Okay. So the way okay. So example.
So would the BMI be the predictor?
So I would say the BMI is our response. It's the variable that we're measuring. So BMI, as numeric, and our predictor could be gender. So this would be t-test for independent groups. Okay. Example 2, our response could be BMI as categorical, and our predictor would be gender. And now we have chi-squared test for independence. Okay, why don't we take a short break here?